Hi, my name is Louise Campbell and I work for Marine Scotland Science, and during this presentation I will talk about a collaborative EU-funded project between us at Marine Scotland Science and the National Oceanography Centre in Liverpool. The project is funded by the EU through Mercator Ocean, who are responsible for managing and delivering the Copernicus Marine Environment Monitoring Service, or as many of us know it, CMEMS. The Scottish Shelf Waters Reanalysis Service is a downstream service of CMEMS and provides a 25-year hindcast of the Scottish Shelf model. So first of all, I'd like to start with discussing the reasons why we need these regional hydrodynamic models. So the objective with a hydrodynamic model is to, as accurately as possible, simulate the water circulation on a temporal scale in a predefined region of interest. And typical outputs from a hydrodynamic model includes currents, sea surface elevations, temperatures, and salinities. This allows you to get an understanding of the variation across a large area over a specific time frame. So measurements are great and they give you lots of information, but that information tends to be focused to a specific location at a specific point in time, or a restricted time period at least. A hydrodynamic model allows you to predict what has happened in the past, but also what could happen in the future, or what could happen under extreme conditions such as different climate change scenarios. So in theory, you can run a hydrodynamic model for any point in time, for any location. In practice, it's a bit trickier, since you need a lot of information about the bathymetry and also access to appropriate data to force the model with. As you can imagine, these models can be very important in a wide range of scientific studies when looking at, for example, transport patterns, connectivity between different regions, population dynamics, epidemiology, climate change, etc., etc. And these type of models and the information you can gather from them support the development of many socioeconomic sectors, such as aquaculture and marine renewable energy. The main driver for us at Marine Scotland Science to utilise hydrodynamic models like this is due to our commitment to identify potential economic development areas in the coastal and offshore marine environment while avoiding conflict among users and ensuring sustainability. So as an example, a hydrodynamic model can be an extremely useful tool when generating an environmental impact assessment before installing a new fish farm or a new wind turbine site. These hydrodynamic models provide us with evidence-based input, which can be very important. It was formally identified that there was a requirement for a dedicated hydrodynamic model covering the Scottish waters in 2009. What was available at the time just wasn't good enough. The existing models were either of too low resolution or didn't cover the whole area of interest. So this is how the Scottish Shelf model was born. And the idea behind the model was to develop a high-resolution hydrodynamic model covering the whole Scottish continental shelf waters. And the idea would be for it to be a tool that would be managed and used by Marine Scotland Science, but also contribute to a community model where the scientific community would contribute, use and develop the model according to their own specific requirements, which could then be fed back and shared within the community. So the development of the original Scottish Shelf model was an external contract funded by the Scottish Government, and the contract was shared between CH2M Hill and the National Oceanography Centre in Liverpool under the guidance of Marine Scotland Science. It was decided that the Scottish Shelf model should implement a hydrodynamic model called FVCOM, which stands for the Finite Volume Community Ocean Model. This is a three-dimensional open source model available for the marine modelling community. And one of the objectives with the Scottish Shelf model was that the model should be able to be further developed in-house, and by using FVCOM, this is possible. One of the benefits with FVCOM is that it utilises an unstructured grid. So with a structured grid, you would divide your domain into equal-sized squares or pixels, but in an unstructured grid, you divide your domain into different-sized triangles. So with a structured grid, you have to commit to the same grid resolution throughout your domain. With an unstructured grid, not only are you able to resolve coastlines better, but you are also able to vary the resolution across your domain. So instead of committing to the smallest resolution required in a particular location across the whole domain, you can adapt it according to your requirement, and this saves a lot of computational effort. Another benefit with FVCOM is that there are already built-in features which can be utilized, such as wave modeling, particle tracking, or sediment transport. So the development of the Scottish Shelf model was divided into 3 stages. The first stage of the project was to develop a wider domain model which covers the whole of Scotland. The final domain that was agreed on is highlighted here, and the resolution within this domain tends to be around 1 kilometre along the coast to about 10 to 20 kilometres further out at the boundary. The water column is divided into 20 equally spaced terrain following sigma layers, so each layer represents 5% of the water column. The next stage of the development was to generate some smaller domains of finer resolution. These were all identified as areas of particular interest. So the first domain that we have is the Pentland Firth and Orkney waters, which was identified due to the interest in renewable energy. We then have the St Magdalens Bay, the Wide Loch Linnhe and the East Coast Lewis and Harris model. These were all identified due to the interest in aquaculture. And the resolution in these domains are typically in the order of hundreds of meters, and in these areas only 10 sigma layers are adopted. These case studies or subdomains are nested within the wider domain and can either be forced by the wider domain or run independently. The final part of the initial development was to combine the output from the wider domain and the smaller domains with finer resolution. This way you would be able to take advantage of the finer resolution in all areas at the same time. So this was done by basically slotting in the smaller domains into the wider domain to generate a new integrated mesh. So to the left here we have the wider domain grid, and to the right we have the same area but displaying the East Coast Lewis and Harris grid. As you can see, the grid resolution, especially around the islands, is a lot finer in the East Coast Lewis and Harris model. So these two grids can be combined to generate a new mesh which looks like this. So this grid combines the high resolution around the islands and the coarser resolution further out. By then including output from the wider domain and the finer domain, using a bit of clever interpolation and buffer zones, you can generate a new model output product which takes advantage of both the smaller domain's fine resolution and then the wider domain's coverage. So this is especially important when running some particle tracking simulations where you really need the finer resolution along the coast, but you also want the particles to be able to travel from one fine resolution area to another. So for example, a particle could travel from the Wide Loch Linnhe domain to the East Coast Lewis and Harris domain, through the wider domain to the East Coast Lewis and Harris domain, and then to the Pentland Firth and Orkney waters domain. So this integrated product can be very useful in situations like this. Since the completion of the project, which I think was around 2016, we at Marine Scotland Science have facilitated further developments of the model, and in collaborations with PhD students, postdocs as part of various projects, or just in-house, we have continued to work and improve the model. And the domains that we have added since the original project was completed are the Firth of Clyde, the whole Shetland, the Moray Firth and the Firth of Forth. We have run the model for various time periods depending on different project requirements, but the main output from the Scottish Shelf model to date is a 1-year model run using climatological forcing. So all forcing has been averaged over a 25-year period and run for one single year, and this has been done for all of our case study areas as well as for the wider domain. And for the wider domain, this has also been done for a future climate change scenario where the worst case of business as usual scenario has been implemented. The benefit with the climatology that we have today is that you only have to run the model for one single year and you get a product which represents average conditions. The disadvantages with this is that you lose a lot of information in terms of seasonal and annual variability, and in some situations this can be very important. As an example, storms, which can have a large effect on the hydrodynamics, are all smoothed out over a 25-year period, since they don't always happen at one particular point in time every year. In some situations, it can be very important to capture this information, especially when doing tidal energy resource assessments or connectivity studies which rely on particle tracking over the winter months. So this has limited the potential usefulness of the Scottish Shelf model. And this takes us to the Scottish Shelf Waters Reanalysis Service. So the objective with the Reanalysis Service was to produce a 25-year Hindcast model run of the wider Scottish Shelf model, where the model is forced using CMEMS products. So this is why it's called a CMEMS downstream service. As I mentioned earlier, this is a collaboration between us at Marine Scotland Science and the National Oceanography Centre in Liverpool. And the model runs have been developed and are executed by NOC, while Marine Scotland Science are responsible for the dissemination and demonstration of the service. And as a result, we will have 25 years worth of model output spanning from 1993 to 2017, and this will include both hourly and daily means of currents, sea surface elevations, temperatures and salinities. And most of the data will be available for download at the end of November, and the data will be freely available to anyone who wishes to use it. An improved product like this, which includes the interannual variability, will improve accuracy and also increase the usefulness of the Scottish Shelf model. So the existing climatology, where the forcing has been averaged over a long time period and then applied to the model, running the model only for a single year, is hard to validate since you can only really compare it to other climatological products. And with this new Hindcast, you can perform a more extensive validation, which will increase the user confidence. So we are really hopeful that many will benefit from this improved 25-year model run of the Scottish Shelf model. So in total, there are 6 CMEMS products used for the Reanalysis service, all listed here. These have all played a vital role in generating a product with high user confidence and accuracy. So this list includes a combination of other hydrodynamic models as well as some observational data sets. So to generate the boundary conditions, the majority of the information has come from the Met Office AMM7 model, which is a hydrodynamic model with a 7-kilometre horizontal resolution. And for the assimilation and the calibration and validation, the data products that have been used are based on observations. Some applications will really benefit from this new product, especially applications where interannual variability is important. I thought I would mention a few to give you a flavour of the versatility of the model. So first of all, we have assessment of the impact of renewable energy installations. So this will include things like assessing and modelling how much energy you can extract from tidal turbine installations and what possible effects this can have on both near field and far field hydrodynamics. Another example is using the Scottish Shelf model for connectivity studies for aquaculture benthic species within marine protected areas and other habitat areas. So this involves using the output from the model to force particle tracking simulations, and this allows you to predict connectivity between different areas for different species. And this has previously been done looking at, for example, sea lice dispersion, horse mussels, and flame shell habitats. Another thing you can use the Scottish Shelf model for is to force smaller local models. We do this in-house to force our subdomains, and others do it to force their own smaller local models too. The Scottish Environment Protection Agency, SEPA, used the SSM to force their MIC models, which they then use to determine the suitability for an aquaculture proposal based on the resulting waste dispersion from multiple sources and the risk posed to sensitive features. So this is regularly done by SEPA when screening new aquaculture site applications. The model output can also be used for emergency response in the case of, for example, an oil spill in the North Sea. There's loads of other applications where the Scottish Shelf model can be used, and it's already playing a vital part in many research projects. We hope that this extended model run will increase the range of Scottish Shelf model applications. So this might all sound great to you, but the question is then, how do you access the data and how is the data stored? So the data is stored in NetCDF files. So NetCDF files are very common in the atmospheric and ocean science communities and tend to be used for array-oriented scientific data. The files include both dimensions, variables, as well as metadata. So you can get a lot of information from each data file, which when working on this type of data is very useful. But to read the data, you have to use a software or a program which can handle NetCDF files, such as Python, R, or MATLAB. If you're interested in finding out more about the Reanalysis service or you want to access the data, you should go to our website. On our website, you will be able to find more information about the Reanalysis service, but you will also be able to find a link to accessing the data. And this link will take you to a form which you have to fill in. And after completing the form, this will trigger an email with us and we will get back to you with information on how to actually access the data. So basically, we have to generate login details for you to give you access to the data. If you have any further questions about the Reanalysis service or the Scottish Shelf model, you can also send us an email and we will do our best to try and help. Thank you.